improve the our sort of sustainable endeavors for resources on Earth and on other planets as well. So before I get into it, I thought I would just introduce myself a little bit. My name is Braden Borg, and I've been working at Fleet now for a few years, nearly 3 years. And I've got a background, as you can see, in robotics, mechatronics, and aerospace engineering. And I've always had an interest in sort of combining other disciplines or utilizing my skills and my my sort of interests in robotics and aerospace engineering, space engineering as well, in other fields. And as you can see, I've done some work in artwork conservation, but also some work in space exploration on AI for rovers and improving their exploration capabilities. And it sort of happened naturally, I suppose, working at Fleet, where I've managed to gain some new skills in fields that I didn't think that were going to be available to me, and some excellent opportunities, and be able to lead some interesting projects. And these projects are sort of very similar to some of my past experiences, where combining different fields, scientific fields and engineering fields, other fields of technical applications, can be very sort of prosperous. And I also wanted to touch on who we are and what my company is up to, what we're doing here in Australia. So Fleet has been around now for about 7 years, and within that time we've launched 7 small satellites. And it's very interesting for us because Australia has had a very very dynamic history in space, whether it's been aerospace, launching rockets, or even launching spacecraft for all sorts of different orbital applications. And we've been around for a fairly long time relative to what Australia has accomplished within the last 5 to 10 years. And we've seen a lot of excellent sort of development in Australia's space capability. And we're also wanting to contribute to Australia's economy and demonstrate what we're capable of doing. So we're just a small startup, and very recently we hit 100 employees, and we're now got a very strong company focus on this service, this product that I'm going to be talking to you about. And we're also interested in wanting to make the world a better place from the perspective of having data available using low power satellites, but also mitigating the impact of carbon emissions and how we can sort of contribute to that energy transition. So that will sort of become a little bit more clear in the explanation of what our product is. Fleet is also growing quite rapidly, and we've got a few different sites across Australia, but also international as well. And we just recently opened up a new space in Luxembourg, so as well as being in the United States and Canada. And Fleet has this big, hairy, audacious goal of connecting the Earth, Moon, and Mars. And we've got a lot of experience in the industrial Internet of Things, or IIoT industry, and how we can utilize low power satellites to move sort of data from remote locations, and how that can be utilized for various different types of industries, whether they're utility industries like power and energy, or if there are other industries like agriculture and mining. So we sort of foresee our satellite and that network capability to be usable as a way of connecting between different planetary bodies, and also providing some of the exploration tools for those planets. Now, the satellites we've developed have grown over the years, and we're also accelerating the rate at which we're manufacturing them. So very typical of Australian space companies, we've started off by developing small CubeSats or nanosatellites, and wanting to sort of utilize low-cost hardware and relatively inexpensive launch costs as well to gain value out of having a telecommunications satellite in space. But as we've matured over the years, we've also matured our satellites design, and they've also increased to improve or increase the capacity to send and receive data. And we'll be launching more and more of these satellites as time moves on. We have traditionally launched with SpaceX and Rocket Lab, but we sort of have had a slight delay recently with launching multiple satellites at once, actually. So that's going to be very big for us, happening later this year. So that's been pushed back a little bit, and it might change again, but it's going to be very exciting for us because it's the first time we are launching multiple satellites at once. And it's indicative of our capability of building more satellites and starting to contribute to this constellation which we're building. And this constellation is going to be around 300 of the Centauri satellites. So these are the satellites which you can sort of see up here, this series of satellites, Centauri 6 to 8, which is that latest iteration, that latest generation. And we're wanting to build this constellation for several different reasons, but the primary reason being that we want this data connectivity, and we have a product which utilizes this data connectivity in near real time. So we need to meet the requirements of that data latency, the backhaul latency, and also that sort of global connectivity. So not just for Australia, but around the world as well. Now, I'll talk about Exosphere. So Exosphere is our primary service that fleet offers, and it is exploration at the speed of light. So this is a very interesting application of, well, as you'll sort of soon see, geophysics and space technology, something that has sort of come as an aggregation of fleet's earlier capabilities in IIoT. So that's Industrial Internet of Things and low power satellites to connect low power devices in remote locations, and also exploration techniques that are used in the mining industry, but also for other environmental reasons. So Exosphere is composed of several different primary aspects, and they can sort of be broken down by the technology that's actually enabling the service, and also the technique and later the visualization or the data science aspect of it, which generates the outcome of the product. So starting there on the left, we have satellite connectivity and edge processing or edge computing, and that's basically the technology pulling data out of the field and doing some clever processing, terrestrially doing clever processing to minimize the amount of data that we actually have to pull over these satellites. And the data that we're collecting, so this is all seismic data, and I'll touch on that in a little bit, is sort of used in a technique called ambient noise tomography. And that technique allows us to do mineral exploration. So with some clever post-processing, this all happens in the cloud, we can actually build subsurface images of where we've deployed these sensors. And so we get this nice gradient map here, which allows us to do this type of exploration. So all of these different faculties sort of add together to combine to be Exosphere, and we have different technologies sort of in different aspects here. We have the terrestrial sensors, we have our satellite technology, and then we have all of the cloud processing stuff happening in the background. So ambient noise tomography is a passive exploration technique, and it utilizes something called ambient noise. So this is a type of seismic signal which is essentially ever present within the ground, within the Earth's sort of different layers of soil, crust, and rock, and it's generated by several different factors. Some of these factors are obviously generating stronger seismic signals, such as anthropogenic activities, so mining sites, close to vehicles, cars, housing, anything like that that's generating a lot of noise and vibration gets transmitted through the ground, and we can detect that with seismometers. We also have the generation of ambient noise from natural processes, such as the ocean swell. And that type of signal, despite not being very strong or as strong as the anthropogenic signals, we can detect these signals hundreds of kilometers away from their source. So they're very, very useful signals. And even in remote locations, we can utilize that information to conduct our ambient noise tomography. And ambient noise tomography is not a new process, or it's not a new technique. It's been around for quite a while, but it's one of those techniques that hasn't really, or hadn't up until this point, really developed with newer technology. So sort of low power networks being able to sample data and do some clever processing that can actually allow it to be transferred over satellites. And we get this real-time aspect to these sensors, which would otherwise take weeks, if not months, to collect, and also wait for these sensors to come back and do very slow and tedious data downloading. So we've sort of revolutionized this technique by adding real-time data to it, satellite connectivity. And this gives you another overview of Exosphere. And breaking it down into the technology itself, we have the terrestrial sensors, and this is a sensor that we've developed in-house, and it's called the Geode. And these devices are satellite enabled, so they communicate as any sort of satellite enabled device might do, very similar to an Internet of Things network, and they communicate up via satellite, which backhauls the data, and that enters the cloud where it can get processed and turned into those lovely three-dimensional maps, which are so important for mineral exploration. Now, the Geode itself is our primary product, and it's an interesting project historically for a space company, but it's something that we did a lot of research into and had a lot of opportunity to sort of develop. The Geode is a smart seismometer, so we label it as being smart because it has the ability to do some pre-processing or do some processing of the raw data that it collects. And this raw data is essentially vibration, so seismic vibration induced by its sensor. And it does all this on board on a sort of low power system. And that data is then sort of pushed to the satellite modem where it can find connectivity via the satellite. And so we can do some other very interesting things here. Not only can we pull data out in near real time and monitor the health of the sensor and its sort of contribution to this network that they're deployed in, but we can also send messages down as well and change the behavior or do configuration changes as necessary. So the technology is very interesting from a control point as well, where we get very critical information quite quickly, and we can also adapt the sensor to the environment if it's needed, whether we need to shut down the sensor or change some of its parameters. So the Geode is composed of these different components, and each seismometer is sort of an independent sensor. So each of them do not rely on one another, but the data itself needs to be sort of synchronous. It needs to be the same or the same sampled data across the network. And we accomplish that via GPS time synchronization. So obviously we have the satellite modem there, which actually does the transmission of the data that's collected by the geophone. And the geophone itself is located right at the base of the sensor. So the geophone is very interesting. It's a very rudimentary sensor. It's sort of a mass and spring that's surrounded by a coil, copper coil, and essentially any vibration induced in that mass, which causes it to oscillate, generates an electric signal. And we record and digitize that signal, and then we do some onboard processing, which is all run on a low power embedded system. So there's no operating system running on this device. It's all running on microcontrollers and printed circuit boards that we developed here at Fleet, so that we can actually condense this data. So one of the primary issues that we identified with the seismometer technology, which was traditionally used for ambient noise tomography, were sampling very broadband, very high sample rate, and the data was all completely raw. Now, for an academic endeavor, for an academic project research, obviously it's very important, and that data, you sort of want to make sure you're not missing anything. But in terms of feasibility for a product, we learned that there's a lot of information that we don't actually need from essentially the raw data that gets sampled, or the raw data that's actually measured by the geophone itself. And then we can cut down a lot of that, do a lot of significant data compression so that it's actually suitable to be transferred over a satellite. And this is also very important because the more data that we send over a satellite, or the more of these sensors that we have in the field collecting data and sending over a satellite, the more expensive it is. So we sort of found a balance of number of geodes for an array to do this exploration, and what we can sort of accomplish, or how much data we can transfer back by doing this onboard pre-processing. Each of the devices are also completely rechargeable. So this is very handy. It's very typical for an exploration service where you want to put these sensors out into the field, and these sensors are sort of deployed in an array. It doesn't necessarily have to be a square array. It can be any type of shape. But if there's a region where you want to explore an image, you set out the sensors, and then within a few days, all the data that's collected by these sensors, you can start to generate a very stable subsurface image. And each of these devices are all sort of running their own processes. And we sort of found that around 50 devices, 50 to 100 is very good for the type of exploration we need to do. It's also worth noting here that the great thing about ambient noise tomography is that as a technique, by understanding the types of seismic signals we're looking for, we can actually change the focus of the exploration to the geology as well. So if we need to image deeper, or if we need high resolution data, we can actually change the spacing of these geodes, and we can also configure in the cloud what frequency aspects or what other aspects of the data we want to actually filter out and focus on. So it's a very important job to have geophysicists sort of involved in this process, and we do here at Fleet, who help build this product, to identify what is the type of geology that we're wanting to image, and how we can sort of improve the quality of the product for our customers by doing this type of post-processing, despite the geodes sort of collecting all that data agnostically in the field. So the other really exciting thing about this technology is that we get to learn a lot about the different sort of strata, the different sedimentary structures of the area in which they're imaging. So for identifying minerals, it's usually quite straightforward if we know what we're looking for, because the interesting thing about seismic signals is that as they travel through the ground, they have a higher velocity, or they travel faster through denser materials. And what we're looking for in the subsurface images is the contrast, or the differences in velocities of these signals which are being recorded over a few days period of time. So we can start to map out that type of stratigraphy and different types of structures within the surface. So we're also very excited to hopefully one day put these sensors on other planetary bodies, such as the Moon and Mars, and be able to conduct the same type of analysis to provide a mapping, albeit a relatively low resolution mapping, but still a mapping of the subsurface, and to highlight different areas of interest, whether they're different types of mineralization or the different types of sort of underground stratigraphic structures as well. And that's it. Thank you for listening.
Perfect. So thank you, Braden, for the awesome presentation and just explaining how your company is again working on those solutions and providing those insights. So and also thanks for staying here late. And I know it's already almost 1 a.m. right in Australia. So appreciate that. So there is a question as well in the chat, and we still have some time, so we can cover that, I guess. Olga is asking, are you planning to use ANT to explore the planets of the solar system?
Yes, well, that would be fantastic. We would absolutely love to. And once again, the technology is sort of built in a way that as long as you have a source of seismic noise, you can do this type of exploration. And what is very interesting about the moon, for example, so as I sort of spoke to just before, the ambient noise on Earth is generally and most strongly generated by anthropogenic sources. So, man-made activity, cars, vehicles, machinery, that type of stuff. But on the moon, we don't have any of that. So what's interesting on the moon is that apparently events such as meteorite strikes and other types of impacts can generate vibration, and those impacts can actually generate a strong enough source that we can do this type of exploration. So even on these types of planetary bodies, we're expecting to be able to do this type of exploration.
Perfect, wonderful. So thank you for that and explaining that in detail. And my next question for you, Braden, will be, as an aerospace engineer, how did you approach the design and development of the Geode to ensure that it can withstand, again, the harsh environments?
Yes, it's a very good question, and we've sort of learned this through different versions, different sort of generations as well. But for us, the primary focus, and this is something that we only learned by doing a lot of field work, is that sort of moisture ingress and water is a primary source of issues. So basically, building something that's relatively strong and rigid is important, but water sealability as well is also super important. We also deploy in very harsh environments. So in Australia, it gets very hot, but a lot of other areas of interest around the world for mining, that is, are in locations such as Canada and even some other parts of sort of United States, and it gets very, very cold. So that's another challenge. Thermal control and management is something that we're continuing to improve so that we can make our sensors more robust for those environments.
Perfect, wonderful. And can you also speak to any of the, let's say, cost or efficiency savings that have resulted from using the Geode and its satellite-enabled technology for mineral exploration? And how would that compare, let's say, to traditional exploration methods?
Yeah, absolutely. So traditional methods actually use a variety of different techniques, and ambient noise tomography is only one of those techniques, but the technique itself, or the way it's been used, is very, very slow. So they send out traditional sensors, or sensors which you put into the ground, they just log data locally, and they leave them out there for weeks. The biggest issue with this is that you have no visibility of the data whatsoever. So you don't know if you're exploring the right area, if you've found something, if the data is good. And you sort of just have to leave the devices out there because it is such a logistical challenge to go out and deploy these sensors and move them around. But with the Geode, because they're satellite enabled, we see the data almost immediately. Like, in terms of satellite real-time data, we're talking minutes, right? So we can see the quality of the data and we can start to build that out pretty much as soon as it starts flowing.